Okay, what can we offer here? Before we jump into this, some ideas, some things worth noting or thinking
Turn
about.
your f of x into a pi.
Okay, we can. Yeah, I mean, if you wanted to try to solve for g of x, we'd turn f of x into a y, flip x and y, and solve for x, right? We could do it. What are we going to get for our answer? I mean, what is the inverse of x cubed?
Square. I mean, cube root of x.
Cube root of x? Yeah. Or x to the 1/3, same thing. Okay. You're right. We could cheat this time, couldn't we? Well, let's explore that a little bit. How about if we graph those two functions on Desmos, and we'll just play around with this a little bit and see what we get. Okay, so there's f of x, right? That's our cubic function. Everybody agree?
Yeah.
Okay, I've defined g of x. Well, g of x is just the inverse of f of x. So there it is. It's x to the 1/3. Does that make sense?
Yeah.
Do they have the right kind of symmetry?
Yes.
Yeah, they do. They're reflective symmetry over the line y equals x, right? Okay, let's just demonstrate that real quick. So let's make that green. Right, so they have reflective symmetry over that line like we'd expect. Okay, we got that. Now we're trying to we want to find the equation of the line tangent to the inverse at x equals 8. Okay, so let's explore this a little bit. What happens if we plug in a value 8 into our inverse function? We're going to get back 2, aren't we? Right? Everybody agree? Okay. So I could if I plot the point 8, 2, sure enough, it ends up on our inverse graph, doesn't it? So there's the graph we're looking for. Okay, what's the corresponding point on the original function? 2, 8. Okay. So what if I'm going to let a equal 2. I'm just going to type it in. If a equals 2, and we're going to say that, actually I'm going to let a equal 8. And b is going to be g of 8, right? And so I don't even really need that point. I think I've already got it graphed here. So there's the point AB. Agreed? Okay. Let's make that blue, though. Okay. The corresponding point for the function, the reflection would be what? Would be BA, good, right? So that's going to be this guy. We're going to flip those around. And let's make that one red. If I want to come up with the equation of the tangent line, well, I've already got the point of tangency. That's no big deal, right? It's just 8, 2. It's going to be what I get when I transpose the x and y coordinates of my original function. Okay? So could we come up with, without having to have cheated here, and found explicitly what the inverse function is, could we have figured out what both coordinates would be just based on the original function? So we know the value we're inputting into the inverse function is an 8, right? So how could I use the original function to find the other part of that ordered pair? Why don't you think about that for a second? Right? I know that the point of tangency, I need a point of tangency. For my g of x function, I know that that's going to have an input value of 8, but I want to find the output value. Yes, sir? Okay, good. That means that for the original function, right, for f of x, that 8 would have to be the output, and I'd be finding the input, right? Because they have to go together. That's the definition of inverses. Inverses transpose domain and range, right? So we could go up then to our original function, and we could say, okay, well, if the output is 8, we just get the equation x cubed equals 8, which we could solve. What do we get? 2. So if we know x is 2, that's the input that goes with the output 8 for my original function. So for the inverse, 2 must be the output. So we have a point of tangency. Do you agree? We haven't had to really, once again, we're not using the fact that we know what the inverse function is, right? Okay, so that part's done. Now the second part might be a little trickier though, right? Because what are the 2 ingredients we need for a tangent line? Point and the slope. We got the point. There's the point of tangency, but now we need the slope, right? So let's investigate this a little bit. Let's go back to Desmos and see if we can come up with a relationship that we can use here. Okay, so we know that those 2 points go together. Well, we know what the original function is. I'm going to pretend we don't know what the inverse function is, though, right? At least for the moment. So if I want to come up with the equation of, if I want to come up with the derivative of the original function, that's easy. 3x squared is my derivative, right? And so we can calculate, if I define capital F as being f prime, let's plug in, well, actually right down here, we can just do f prime of b, which is 2, right? If a is 8, we define b as 2, okay? So f prime of b is 12. That looks about right, doesn't it? It's a pretty steep slope. And if I graph the tangent line, uh-oh, what happened there? I think I got this messed up. I think that's supposed to be an A. Oh, I did? Oh, I got it. I think I got it backwards here. I think it's, maybe I did. Let's try that again. That was a B, right, at first? No, that can't be it, though. Neither one of those is working. I gotta fix that. Darn it. So that's supposed to be an A, and that's supposed to be a B, I believe, and that's supposed to be a B. There we go. Okay. So there's my tangent line, right? Does that make sense? Y minus A is my output, isn't it? A was 8, right? And that's the Y coordinate. So that's Y. It's essentially that's Y minus 8 equals F prime of 2 times X minus 2. Yeah, that's point slope form, isn't it? So there's the equation of that tangent line. Okay. Well, let's just see what happens here. If I'm not even doing any math, but if I were, well, I guess I did. We're going to cheat first, and then we'll reverse engineer this. We're originally going to think about the explicit value of the inverse function, which is the cube root of x. So if I were to calculate g prime of 8, what do you know? I get 1/12. And if I graph the tangent line, let me fix this first, which would just be y minus 2 equals g prime of 8 times x minus 8. Look what happens. What do you notice about those tangent lines? Yeah, look at that. They're also inverses, aren't they? Don't they have to be? I mean, if you think about this, if the orange tangent line, if I'm between any 2 points on the orange tangent line, if I'm going to rise by P and run by Q, when I interchange the X and the Y, isn't that just going to reverse the rise and the run? Because rise is a change in Y and run is a change in X, right? So doesn't it make sense then that if the rise over run was like P over Q here, it'd have to be Q over P down here? Because I'm just flipping the variables. You start to see that there's a huge amount of symmetry between these inverses then, right? So that tells us something pretty important. That tells us that the derivatives at the partner points here, right, for the inverses are reciprocals of each other, right? Okay, that's huge. That's huge. So we should be able to make a prediction then of what the slope of the inverse function is at a point without ever even calculating it, right? So let's go back and think about that a little bit. And we gotta go slow because there's a lot of moving parts on this, but you see where we're going with this? Get an idea? So if we want to calculate, we need to find the slope of the tangent line. Right, that's our next task here. We got to find the slope of the tangent line. We got the point of tangency. Now we need the slope of the tangent line for g of x, right? But what did we decide? The slope of the tangent line for g of x, how is that related to the original? The reciprocal, right? You gotta be careful about the inverse, because we're talking about inverses here, right? So it's reciprocal. So we know that the slope of the tangent line for g of x is going to be related to the slope of the tangent line for f of x, right? Okay, we know that the slope of the tangent line for g of x, how are we going to make that relationship? So g prime of 8 has to equal the reciprocal, right? So what's that mean then? It's going to equal, but if it's a reciprocal, I got to do 1 over f prime of what though? Of 2, right? Good, of 2. Not of 8, it was of 2. Okay? Well, how is 2 related to 8? 2 is related to 8 because they're partner points, aren't they? Now, I don't want to write the relationship between 8 and 2 in terms of the inverse because theoretically we haven't even calculated the inverse yet, right? But if the point of tangency for the blue line was 8, 2, the corresponding point of the corresponding point for f of x was 2, 8, right? Everybody see that? Mm-hmm. So if I want to calculate g prime of 8, that's equivalent to calculating 1 over f prime of the other point, which would be g of 8. You see what I'm saying? Okay? So see if, could you come up with a formula for that then? Like we want to just come up with something very general here. Right? If we want to say, just in general, once again, we'll define g of x is equal to the inverse. So I have to write, that's kind of an awkward notation to write f inverse a bunch of times. It's easier if you write it in terms of f and g. If g is the inverse, then g prime of x in general is going to equal 1 over f prime of what? How do I say the other point that goes with x? G of x. That's it, right? If we're defining x as the input to g prime, then the input to f has to be the output of g. You see what we're saying there, right? This is, so once again, this is going to be our input for g, so this has to be the input of f. But what's the input of f? Equals output of g. Get the idea? Okay? So let's try one of these then. Without drawing any graphs or anything here. Let's try... I'll just pull up an example. Okay, we'll do an easy one. We'll do a linear one to start with. So f of x equals just a line, so like 3x plus 9. Find g of x is the inverse. Find g prime of Okay, try that. Partner up, see if you can come up with it. How are we going to do that? Without calculating the inverse.
TI. Something you can't see anymore. That's 202.
Okay, so what's our little trick again? G prime of x equals 1 over f prime of g of x. Good. Okay?
So then, what's R?
Okay, so then if x is 202, what's g of x? How do you know? What'd you get? 4 is right. Okay. Because think now, here's the trick, right? The input of g is the output of f, right? So all we have to do is set, if I want to know what g of x is, I just have to set f of x equal to 202, right?
Yeah.
And we'll just use Desmos for that, right? What's our trick for solving anything graphically? Super easy trick. Well, the way I always do this, and there's multiple ways to do this, but the easiest way to do it is you set y equal to the left side of the equation and you set y equal to the right side of the equation, right? And then I just look for the point of intersection. If I zoom out really, really, really far, actually it doesn't matter because it never crosses again anyway. There's our point of intersection right there, right?
Wait, so then how do you get it?
Right, so I know that the x value of the point of intersection is 4 in this case. And that's really what I'm looking for, right? I want to know when is 6x cubed minus 11x squared minus 6 equal to 202. So there's our answer. Here, I'll put this in the notes. I'll take a picture of this.
4.
Okay, so then if we know that x, the solution to this is x equals 4, right? So that's the input of f of x, correct?
Yeah.
Right? The input of f of x becomes the output of g of x. Right? So all we've got to do then is just calculate what is 1 over f prime of 4. Well, that's easy. We know what f is. What's f prime? 18x squared minus 22x. So if I plug 4 in, somebody, what do we get? We plug that in. So what do we get? 256 plus 2, so we get 284 minus 88. So is it 196? Is that right?
I'm not
200? What did I do wrong? Oh well. Okay, so we get 1 over 200 is our answer. Okay. 16. Oh, that's right. Yeah, 288 minus 88, that's right. Works. Okay. Get the idea? Okay. We'll practice this some more, but I want to do one more thing before we leave. When are we out of here? 25. Okay, so we can take advantage of this idea then to find some other derivatives too. What if we wanted to find, let's say we're going to define the derivative y to be the arc sine of x. Okay, we know derivatives of trig functions, we know derivatives of exponentials and logarithmic functions, power functions, etc., all that stuff, but we don't know the derivatives of the inverse trig functions yet. Okay? Well, we can't do this directly then, because we don't know that derivative rule. Okay? Can anybody come up with maybe a scheme here where we could do this a different way? What do you think? Is there another way to write that statement?
I don't like arc sine.
You know, like arc sines are very useful. So let me ask you this: what could I do algebraically to both sides? What undoes an arc sine? You don't remember this? Okay, this I'm getting some blank looks on the inverse trig functions. Okay, so let's this will be helpful then. This will be a little built-in review. So inverse trig functions are literally inverse of trig functions. So arc sine is the same thing as inverse sine, right? We've discussed inverses a little bit already this year. If I take a function of an inverse or an inverse of a function, what do they do? Like the cube root of x cubed is x, right? Inverses undo each other, right? So I could, if I take the sine of both sides of this function, I'm going to end up getting sine y equals sine of, and I'm going to write this as inverse sine instead of arc sine. Well, what do? Sine and inverse sine undo each other because they are by definition inverses, right? So that's just equal to x. So another way to write this would be sine y equals x. Okay? Why is that better? Well, because we know how to differentiate sine. Okay? We know how to do implicit differentiation now. So if I want to calculate y prime, which is really all I'm doing, right? I want to find the derivative of arc sine. So I'm just answering the question, y prime equals what? Right? Well, let's do that over here, where we're differentiating functions that we know how to deal with. So what's the derivative of sine y with respect to x by the chain rule? So the derivative of sine hand is cosine hand times y prime. Wow, okay, good. So times y prime equals 1. Okay. So then if I solve for y prime just equals 1 over cosine y. Okay, that's not a very good answer though, right? We want our answer in terms of x, don't we? Because our original function was an arc sine of x. Okay? So this is going to be probably good review. How do we take this original relationship, either here or here? It's probably easier to think about it here. And how can I, based on the fact that sine y equals x, how can I write any of the other 2 trig functions, any of the other 5 trig functions, really, as expressions involving x?
You just do
So I could do, y is equal to arc sine x, so it's cosine of arc sine x. You're right, but that sounds complex. It's correct. Remember dealing with reference triangles? Okay, we need to review. The reference triangles are hugely important. They're so convenient. If I wanted to find any of the trig functions, trig functions can always be conveniently defined in terms of a right triangle, SOHCAHTOA stuff, right?
Yeah, yeah.
Okay, so let's build a reference triangle in quadrant 1 of the unit circle, right? Actually, it doesn't even have to be a unit circle. If I build a reference triangle based on this relationship right here, what does that mean if sine y, there's a right triangle, sine y equals x? So y is an angle, right?
Mhm.
So we could call that angle y. What's the SOHCAHTOA relationship then? If sine y equals x, sine y equals, by SOHCAHTOA, opposite over hypotenuse. So that's the ratio of x over 1, isn't it? So opposite of y is x and hypotenuse is 1. So what does that make the bottom length? By Pythagorean theorem.
Square root
So 1 squared plus x squared equals that side squared, right? So that side squared must equal 1 minus x squared, right? So isn't this just square root of 1 minus x squared? And we could get there real quickly, like if I just call this distance right here, if I call it z, for example, right? Then I know that 1 squared plus x squared equals, z squared plus x squared equals 1 squared, right? So z squared equals 1 minus x squared, so z equals the square root of 1 minus x squared, right? If we want to just solve that for ourselves, okay? So that's a z, right? So there's our reference triangle. Well then, what is the ratio cosine of y equal to? Cosine is equal to adjacent over hypotenuse. So I could rewrite this then, y prime, as 1 over square root of 1 minus x squared over 1. Right? So we end up with y prime equals 1 over the square root of 1 minus x squared. We got it. Right? So that's our answer then to what is the derivative of arc sine x. Right? So we know that the derivative with respect to x of y, which was arc sine x, equals 1 over the square root of 1 minus x squared. So what if I want to make this more general, and I want to do an arc sine of u instead of an arc sine of x? That's no big deal. If I want to differentiate arc sine of u, I'm just going to use chain rule, right? The derivative of arc sine of hand, evidently, is 1 over square root of 1 minus hand squared, right? Times the derivative of hand, which is just a u prime. We'll just multiply the whole thing by u prime. Well, why not just put the u prime on top? So we get a new formula. There's arc sine. I could do the same thing for all those. They're all going to work the same way, right? I'm just going to end up setting this up as, writing the function, the arc function or the inverse function in terms of a regular trig function and just differentiating implicitly with respect to x. And I'm just going to get the same. I'm going to end up taking a derivative of a regular trig function, which I know how to do, and then writing the result in terms of my reference triangle. Okay? And if I do that, I'm going to get all 6 of the regular inverse trig functions. Okay?